Hello.
Yes, sir. Hello.
Yeah, hi. So, do you have any questions from last class or last whatever has been done? Okay. So, if not, today's class will be slightly different. Okay. So it will be mm, more like a tutorial. Okay. So I will give you one problem, and you are supposed to uh, solve it. Okay, in your I will give you another 15 minutes or 20 minutes. Solve it in your paper. Okay, and then you are supposed to email me. Just take a photo and send me that. Email me that thing, and then we can have a discuss on that, how to go about it. Okay, and yeah, so possibly there will be some marks associated to it also. So let's start with this thing. So let me first, and please try not to look up the internet, okay, for these solutions and all, because these problems are not like they're pretty easy things that they're in the internet. Um, but yeah, but it is more for your practice and all. So what have we seen so far? We have seen some NP-complete problems. And what all NP-complete problems we have seen? I have told you that SAT is NP-complete. And then we have seen that assuming SAT is NP-complete, we have proved that ILP is NP-complete. We have also proved Vertex Cover is NP-complete. Now, I want you to prove, okay, the first problem is that prove that independent set is called IS, this is NP-complete. Now, what is independent set? I will tell you. Okay, so what is an independent set? Okay, so given a graph G, okay, a V prime subset of V is an independent set. Maybe this is not correct. Is an independent set. Independent set if basically between any two vertices U and V in V prime, okay, this edge UV is not in this set, in the edge set. So any two vertex that you pick, that should not have an edge between them. Okay. And the independent set problem, so IS, so this is says that you have been given input is a graph G and a vertex and a number K, which is a natural number. And question is that output is 1 if and only if there exists an independent set of size of G of size. Now size is basically size of the vertex, right? Greater than or equal to K. So I am not going to say too much about this problem. I am giving you, so this proof is, this definition is there. If you have, of course, some doubts about this definition, you can let me know. But what I want you guys is to use this definition and prove that this problem, this independent set problem, IS, is NP-complete. I want you guys to fill up a pen and paper, think about it, no rush, think about it, and whatever partial and all, whatever you can do, you can do it. Okay, and I want you guys to, right now it is 2:10, I want you guys to write it and give it to me by 2:40. Okay, email me that one so that by 2:40 I will get the emails, and then we can discuss that, what is the proof that is there. Yeah. So today we'll be doing a few of these problems like this, and it will be counted as as one of the internal assignment stuffs. Okay. Is it clear?
Yes, sir.
Sir,
Oh, yeah.
could you please explain the problem once more?
Yes. So the independent set. So did you understand what the independent set is?
Yes, sir. I mean,
So
yeah,
it is a subset of the vertex set, right?
yeah,
So that no two of the vertices have any edge between them.
yes, sir.
Okay. Now, question is that of course you can always have an independent set of size 0, right?
Yes, sir.
Or you can an independent set of size 1, right? One particular vertex. That's an independent set of size 1,
Yes,
right?
sir.
So of course the question is that your goal is to take more and more independent set, right? So
Yes,
the
sir.
problem is you have been given an input, which is a graph and a k, and you have to prove. The problem is that answer is 1 if and only if there exists an independent set of size at least k. So I give you k equals to say n by 2. Question is that does it have an independent set of size n by 2?
Okay.
I give you k equals to 1000. Is there an independent set of size 1000?
Yes, sir.
Yeah.
I have one question. So, for proving that a problem is NP complete,
Yes.
do we need to first show that the problem is at least NP?
Yeah. That's the first part of it. That's a small part of it that you have to go. Yeah.
Okay, sir.
Okay. Good. Okay. So you guys can start thinking about it. And if you have any clarification, I will do it. Need any
Sir,
Yeah, tell me.
so can you suggest what NP complete problem should we use for the reduction, or it can be multiple options would be
See,
easier?
there are three options, right? SAT, ILP, and Vertex Cover.
Yes,
Yeah.
sir.
So, okay, so I can give you a hint here. Okay. Start from SAT.
SAT. Okay. Sir.
Yes.
So can you share your email?
Sorry,
Can you share your email ID?
you don't know my email ID? Okay, so I can just maybe send it in this chat here.
So was there any hard limit on the time, or we can?
No, it's fine. You can take some time. Like I have
Oh,
already got two answers. Yeah. So
I thought there was a. I wasn't able to get the answer. Right.
that's I see that. I just now saw it. But if you want to think some more time, that's fine.
Okay.
Okay. I mean, yeah. Hello, Anurag. Also, if you want to think, you can also think about reducing from vertex cover. That might also be kind of easy. So it's like you can think of either of them.
Yes, I was thinking about vertex cover initially.
Okay.
I wasn't able to get it.
Yeah, the rest of you, I mean, maybe you can take another 5 more minutes, but please try to send something. Okay.
is the construction similar to what we did in ILP?
With ILP,
I mean, so we
I will discuss it in
okay.
just 2 minutes. So let your friend submit.
Not ILP, the vertex improving vertex cover from SAT. We used some.
You can use that, something of that form. Something of
Yes.
that form. Yeah, so I've got 7 answer sheets here. Can you, the rest of you submit? Okay, so I've got from 8 people, and I don't know the rest of you are planning to give or not. Mridul, Ritam, and Ritvik.
Sir, it will take 2 to 5 minutes. I am writing it down, sir. Whatever I have think.
Hmm?
Sir, whatever I have think of the question, I am writing it down. Sir, I am not able to solve it completely. That's why.
Okay. Ritam and Ritvik, are you there?
I am Ritam, sir.
Yeah. So are you submitting?
Need a few minutes, 3 minutes at most.
Okay, I think I will start now. Okay, because I think we cannot wait for any longer. Anyways, Ritam and Ritu, you had joined the class also quite a late.
Sir, I have sent you my answer.
Okay, very good. So first of all, so here was actually a very simple problem. Okay, and actually one of the main thing that happens is that, as I told you, okay, first of all, what is the first step that you are supposed to do? Many of you have got it correct, by the way. Okay, many of you got the whole problem correct. The first thing is to show that independent set is in NP. Now this is kind of easy to show, and I'm not going into it. I'm sure almost all of you have got it correct. Okay, because the witness, or if you have to show such a thing, all you have to say what is the witness, and the witness is the independent set. Right. So witness is basically a set, is a subset V prime, subset of V, such that size of V prime is more than K, and V prime is an independent set. And all that you have to check is whether the witness is correct, meaning you have checked that whether this V prime is indeed bigger than K, and whether V prime is indeed an independent set, and both of them can be done in polynomial type. If you just write it this thing, we are good enough. You don't have to give an algorithm or something like that. Okay. Now for the other problem. Now this is where things are interesting. Okay. See, there is all you have to show is that you have to show the SAT can be reduced to vertex cover. No, not vertex cover, to independent set. Or you can show vertex cover is less than independent set. Or you can show anything, ILP is less than independent set. Either of them, any of them is fine. So whenever you are faced with this kind of a problem, the first thing is that, see, all of them are correct. If I am telling you to prove that independent set is NP complete, you know that there must be a proof that helps us to prove this. There must be a proof that helps us to prove this. There must be a proof that helps us to prove this. But it's all about which proof is easier to prove. Okay. And that is something that is not 100% clear, and it depends upon various things. And so what you have to do is that you have to kind of guess, or kind of say that, okay, which is the kind of easier thing to prove, okay, and then accordingly prove it. So let me tell you, first of all, many of you have used this particular thing. Vertex cover is less than independent set. Now that is a very easy, nice one. So what do you have to do? You have to prove, if you want to prove that vertex cover is less than independent set, the idea is that you are given, so you better to kind of write it down. Okay, so given a vertex G, which is V comma E, and a K, I want to produce a G prime, which is V prime comma E prime, and a K prime. Okay, such that, what is it that we want to say? That G has an independent set, so a vertex cover of size less than or equal to K, if and only if G prime has an independent set of size bigger than or equal to K prime. Right? So this is what you are supposed to prove. Okay, so so note that this is what is given to you, and this is what you will produce. It is not the other way around. That's something very important. So you start from a graph and a G. Now many of you have observed a nice graph theory property. Okay, what is it? Many of you have proved this kind of a lemma or statement or whatever, that if S is a vertex cover of G, or forget S, if S is a vertex cover of G, means S, what is it? S is a subset of V. If and only if the S complement or V minus S is an independent set of G. Now, many of you, this is the graph theory condition, and this shows, if you have proved this one, this shows that you have understanding of vertex cover is good, your understanding of independent set is good. Possibly you remember it from somewhere else, just whatever it is, but you understand those two things. And once you prove this statement, okay, now I'm not proving this lemma. I mean, you can want to, if you can go back and prove that lemma, this is, once somebody says this lemma, it is not hard to see how to prove it. But once you do it, then what is this thing? So you have been given G equals to V comma E comma K. What is my G prime?
So it equals G.
G prime equals to G. And what is K prime?
N minus K.
N minus K. And that's it. Right? It's kind of this lemma. Once you have this lemma, this is obvious then. Okay. Now this is a very nice proof that you can do. Now, what about the other one? Could you have done with the other thing? Yeah, go ahead. Somebody wants to say something.
In this, we can also show that this transformation is reversible, right? This.
What do you mean reversible? Yes. I mean, this transformation is reversible. You could have used this transformation. So if you knew that independent set is NP complete, then you could have used this to prove vertex cover is NP complete.
Right, right.
This particular transformation is a kind of a reversible transformation. Okay. Now, what about this one? The SAT is less than vertex cover. Sorry, independent set. Now, this is again not too hard, by the way, but this requires some kind of a gadget construction. So you kind of remember what those, I mean, when we did that graph, in some sense the graphs are same, basically. I mean, now that you know it, kind of. But more importantly, I mean, you could have used the same kind of reduction to see what happens, right? Namely, if I give you a SAT, okay. Okay, so phi is a formula which is C1 and C2 and Cm, and the Ci is equals to Xi1 or Xi2 or Xi3, and the variables are A1 to An, right? So basically, this Xi's are basically Xij's are basically one of them. I know that A1 to An. Then what do you have to do? You have to construct a graph V comma E and a K such that you want to say that the SAT is satisfiable if and only if the vertex cover is satisfiable. Sorry, if and only if the independent set, there is an independent set of size greater than K. Right. Now SAT is satisfiable, meaning every clause must have at least one term. Okay. And we are talking about independent sets, right? Fine. So at least one thing. And also important thing is that, see, this is one thing that's already there for us, right? Which means that if A1, okay, so sorry, this I made a mistake for here. So X1 to Xi is A1 to An, comma, A1 complement to An complement, right? That if A1 is true, if and only if A1 complement of A is false. I mean, you cannot have both of them true, right? So how to do it? So one way is that, okay, what happens if I, for each clause Ci, I put a triangle. Okay, what are they represented? This is xi1, xi2, xi3. Similarly, I do it for each triangle. Right? Now, good thing is that once I do it for a triangle, what is the useful thing? xj1, xj2, xj3. Is that in this triangle, among these three things, how many vertices can go into an independent set?
One.
One, right? Not more than one, first of all, right? You cannot have more than one thing over here. Very good. Now, the other thing that you do is that, see, say maybe say consider, let's say this is equals to A1, and say this is equals to A1 complement. What should we do? Can both of them be in the independent set? Both of them be same? No, correct?
No, sir.
Yes.
I mean, ideally, the independent set should look like the set of two literals here that is being satisfied, right? So one way is that if, so in this graph, okay, if you draw an edge between these two, then what happens? Then for any two of them, so any A1 and A1 complement, only one of them can be satisfied. So what is this graph? Let's think of it. So G equals to V comma E. What is the vertex? So vertexes are basically, I can think of this is the set of all xi1, sorry, x11, x12, x13, x21, x22, x23, and so on till xm1, xm2, and xm3. Right? Now, what are the edges? First of all, xi1, xi2 is there, xi2 and xi3 is there, and xi1 and xi3 is there. So these triangles are there, right? For all I. And next is that if xij is the complement of say fkl, then so basically if this one and this one are basically the same term, except that they are complement of each other. So this is basically one is opposite. Then I put these two things, I'll put an edge between them. That's not complement. There's no complement in this whole graph. This is in the edge. So that's my how I define the graph. Now let's see what happens here. What is the independent set in this graph? How big is the independent set?
Sir,
Yeah.
sir, in this reduction, isn't there a problem? Because what if there is a solution? So there is a satisfying solution, but it takes, let's say, 2 points from a single triangle.
Yeah. Can it take?
So we won't be able to get any triangle such that it takes two points because of
Right.
the conditions that we set. But
Yes.
but
Yeah.
what if in the satisfiability problem there is a solution, but it is such that there exists some clause which has at least two of them on.
Yeah. So don't take two. You see, this is, I mean, this might be say A2. This is
Yes.
also A2. Nobody told me to take both. Maybe maybe A2 is correct, right?
Okay.
I mean, A2 is correct and A1 is false. Meaning I have to, therefore, I have to take A2 and A1 complement. So this is satisfied, this is satisfied, and I don't need to take this one.
Oh, okay. Right.
So
Yes.
yeah.
Could you please repeat from that part when you considered these vertices and the edges in the next page?
I mean, you want me to explain the edges?
Yeah, no, sir. That's fine. But then after that, what did
Yeah.
we do?
So after that, what is it? What is the property? Let's see, try to understand. Okay, in this graph, what is the independent set? How big is the independent set? Can you say? So first of
So
all, the independent set must be lower than number of so each clause can have at most one thing, right? So it's M, right? Now, when does this independent set is more? Can this independent set be equal to M? Is it possible that the independent set is equal to M?
yes, sir.
Yeah,
What-
yes.
What does it mean? Independent set is equal to M?
So that means
Exactly.
that we have a
In
solution.
all these M triangles, there's no connection at all.
In all the regular triangles, I mean, I can from each triangle I can pick up a vertex, right?
Right.
Such that there's no connection between them.
Right.
Right. Now,
So there is no conflict with regards to the A1 and A1 complement both being included or something like that. Right?
exactly. So if this graph G has an independent set of size more than or equal to M, actually, in fact, exactly equal to M, what does it mean? That means every vertex, every clause, or meaning among this xi1, xi2, xi3, okay, or every triple of vertices you think of, at least, or at least, exactly one of the vertices is in the independent set, right?
Right.
So what does it mean? If it is an independent set, can I produce a satisfying assignment for this thing, for SAT?
So the independent set itself gives us the satisfying solution.
Okay, so why is it this? So if I take the independent set, so independent set matches something, right?
Right.
Right.
So all the clauses are satisfied then.
Yes.
And also there is no conflict between an element and its complement both being included.
So we have to be careful here. So okay, so this will give us a satisfying assignment. Okay, that solution. How?
So in each of those clauses, there is exactly
Ah.
one from the IS.
Yes. If xij is in this independent set and ak equals to xij, then ak is true, right? If I take this one, then what happens? Now every clause has at least one vertex, one literal which is independent, which is satisfied, one literal which is satisfied, right?
Yes.
That is this property that every clause have exactly one vertex.
Yes.
And can it be that I have taken both AI and AI complement, both of them has been satisfied? No, that is not possible. That means if AI and AI complement is satisfied, AI equals to something, right? AI is satisfied, meaning by definition, AI equals to say X, or maybe AK equals to Xij, AK complement is equals to X RTS, right? But because these two are complements, so there's the edge between them. So not both of them. So in that case, Xij, so both,
Cannot be in the independent set.
yes, Xij and XRS cannot be in independent sets simultaneously. Right? So exactly one of them is satisfied, and that's it. So this gives us a solution to this stuff. Right? And what about the other direction? So what happens if I give you a satisfying assignment? Okay, if I give you a satisfying assignment, what I will do is that means every vertex. Okay, first of all, consider every all the vertices which are satisfied, and I put them in the set. Now that is not necessarily an independent set. Why? Because there might be in each of these triples, there might be two things or three things.
So the case where A2 is part of the SAT solution, we can see here that J2 and Xi1 will both be included.
Exactly. So how will you do? Because for every triple, just pick one of them. That's it.
Okay, so this is an additional restriction we impose.
Yeah, we just take only one of them. Okay.
So we can just, so you're saying we can just order all the clauses, and then for, if let's say we encounter more than one,
For any clause, if I have more than one thing, okay,
right?
which means that for a particular triple of vertices, two of them are picked up in the independent set or in the set, I will just
Right.
throw one of them out. That's it.
That
I doesn't mean that throw the other one. Okay, I'm just saying from here, I will just not take this one. I will just take this
so
one.
that is not the SAT problem,
Okay, why not?
because we are modifying the, so we are doing
No,
it in
I am not.
13.
So I am saying that if there is a satisfying assignment, then there exists a independent set of size M. Okay. Okay, so maybe I should do it here. Okay, let's do it properly. Okay. Okay, so let phi be satisfiable. Okay, and let A1 to A k and A k plus 1 till A n complement are true. Okay, so that is the assignment. Right, without loss of generality, I'm assuming that the first k variables are satisfied and the next some of them are not satisfied. Okay, then define this set S, which is a subset of the vertex set, which is basically S equals to all the Xij's. Okay, all the Xij's such that Xij equals to, so maybe let's call this one is set A. So it is a subset of A, is the element of A. So all the sets, okay, so you understand what I mean here, right? No. Okay, so what is this? See, I had these two things, right? I had this set of variables. Sorry, I have the set of the vertices, right? The vertices are xi1, xi3, but xi3 equals to a1. I have also xj3. Xj3 can also be equals to a1 if required, right? So I'm just going to pick up those vertices, look at all the vertices which corresponds to things that have been satisfied.
Okay.
Okay, so this is equals to AK, not AK is not a good idea, AT. Yeah, I think the earlier rotation was better. So this is actually subset of A. Okay, meaning this is equal to some AT, which is equal to subset of A. Now, this, what is the property of this particular set? This particular set is that, okay, this property, okay. Now see, because this phi, because phi is satisfied, is in SAT, what does it mean? That means, and this is a satisfying assignment, so that means take any xi1, xi2, xi3, intersect this one with the S, this is equal not empty. Right? Every triple has at least one element. Excellent. But the problem is that it is not necessarily a vertex cover. So note that S is not an independent set. Why? Because in this thing, I might have more than one. Okay, So what I do is that arbitrarily, okay, so go over all triples xi and throw away all but one element of xi1, xi2, and xi3 intersection S. So if there are two elements, so basically if this intersection is 1, just keep that. If the intersection is 2, throw away 1. If the intersection is 3, throw away 2. Okay. Now what happens here now? So I claim is that, okay, first of all, two claims. Number one, now this set S prime, okay, so let's call this updated set S prime. Okay, so this is after doing so, I have get S prime. So S prime is a independent set. Okay, note that in every triple there are one, okay, at most one now, and okay, in fact every triple has exactly one, right? Because there is everything. So every triple has exactly one. So what is the size of S prime? Is actually exactly equals to M. Every triple has exactly one. And now why is it independent set? Right. So only option is that maybe I have this triples here. This is in my independent set. And maybe I have a triple here. This is also in my set. And can there be an edge between these two? And the answer is no. If there is an edge between these two, this one corresponds to some AR. This must be corresponds to AR complement. And that is not possible, right? There was no edge between.
Yes, sir.
Okay. So good. So so that will show that if you have an independent a satisfying assignment, you can reduce it from SAT. Okay. Now, so what happens is that, so we have seen this problem, independent set problem, and as we can see that there were two different things. You could have reduced from vertex cover, you could have reduced from SAT, you could have reduced from anything. You could have reduced from independent from ILP also. Okay, and it is all about which one you would prefer and which one you know how to prove it or something. So there are basically a lot of proofs and you want to use it to prove it.
Sir.
Yeah.
This also gives us an alternative graph to work the VC problem on.
Yes, it can also be done within that. You're exactly correct.
So that means instead of that construction that we had seen in the last class,
You could have used this construction
and then tried to find a VC with at least 2M.
right. Exactly, you could have done that also.
Okay.
That's very correct. Okay, good. Okay, so now let me go to a slightly different problem. Okay, namely, okay, so this is what we were talking about, the NP completeness, right? If I give you a problem, how to prove it NP complete. But then you have the other issue, right? If I give you a problem and you know how to, you prove first of all you NP complete, how will you solve it? Right, the opposite direction. So say I have a so for proving an language is or a problem is NP complete, what will you do? You want to prove, okay, you show that or you prove that SAT reduces to L. Again, I'm repeating it. SAT reduces to L, or ILP reduces to L, or vertex cover reduces to L, and so on and so forth, right? So you start with a SAT and reduce it, and you create an instance for L. But what happens if I want to solve L? But to solve L, now this is just the opposite. I want to solve L using some known, say, algorithms for, say, SAT or ILP or something. So you have somehow you have got a solution for ILP. Then how will you do it? That time you do the opposite. You take this L and reduce it to integer linear program, and then use the ILP. Or you take this SAT problem and reduce it to SAT. Okay, and then you use the SAT, the algorithm for SAT to solve it. Okay, so these are the two very important things that you should always keep in mind. Okay, now note that this is something I am repeating. I've seen people making mistakes all the time. Okay, say you want to solve a problem L, you have reduced it to SAT, meaning you have used. What does this mean? What does that mean? Use a subroutine of SAT to solve L. Okay, you use a subroutine of a harder problem or a hard problem to solve L. This does not mean, and I don't know how, I mean, I can just maybe very categorically, I want to say it very strongly. This does not mean that L is NP complete. Okay. This does not mean. So in fact, if you think of it a little bit, even simple questions like, is there a longest common subsequence of size k? So what do you think? Is this problem NP complete? Okay. So given the problem, say, given a set of a sequence of n numbers, is there an increasing subsequence of size bigger than or equal to, say, t? What is this question? This question, is it NP complete or not?
Sir, it is P.
It is P. Okay, why is it P?
Because we can do this in n squared.
We can do it in n squared, right? We can solve the longest increasing subsequence problem in n squared or polytype. So this problem is in P. So if I call this problem, say, the LCS problem, the longest increasing subsequence, right? So LI is S problem. Okay. This is in P. Note that LIS is in P. But note that LIS also can be reduced to SAT. Okay.
Yes, sir.
That does not mean, as I again repeat, LIS is NP complete. Okay. So just because you can solve a problem using SAT, or you can solve a problem using ILP, okay, that does not mean that that problem is NP complete. And believe me, I have seen very senior faculties make mistakes here. Okay. So this is something that you should always kind of keep in mind very carefully. What is this reduction? Which is reducing to what? Okay. Okay. So now I have some 20 minutes more of this class. Okay. I don't want to be too much, but I want to just give you, and so whatever I'm going to tell now in this 20 minutes is not actually related to, will not be there in the course. Okay. So this is something much more towards, I mean, since I have gone in this direction for some time. So this is where we have to kind of say that, okay, see, yeah, so I started with this reductions, and how can you finish? How do you solve an NP complete problem? And this is something that's what I will be trying to explain. And again, I will not be solving it. I will be trying to give you some ideas which are mostly for later on. Okay. So you remember this problem?
Yes.
Okay. So this problem we had was like, okay, you have to solve, you have to basically optimize something, right? You have to optimize your amount of people that you can reach while ensuring that you have certain constants satisfied, right? So we kind of wrote it as a ILP solution, ILP, right? Yeah, we wrote this whole thing as an ILP, right? So question was that, oh, great. So this is an ILP and done. But problem was that we got stuck there. An ILP is an NP complete problem. So what does it mean to solve this? Can I solve it? Now, there are certain things. First of all, is that not, see, ILP is NP complete. What does it mean? Okay. Or ILP is not in P. So let's say that ILP is NP complete, which, and from which I can almost certainly assume that ILP is NP complete, from which I can almost certainly say that, I mean, if you write it like most probably, ILP is not in P. What does it mean? Can somebody say, explain, what does this statement mean?
So that we probably won't be able to find a polynomial time algorithm to solve this.
Okay, so good. So what does that mean? What is the polynomial time algorithm? Which basically means that we probably don't have a polytime algorithm.
Right.
What does it mean?
So it's like stating that P and NP are different.
No, but I want to know, I am kind of helping at something else. So when somebody says something like this, what does it mean? So what I'm trying to say is that it means that, okay, what does it mean? That for every polytime algorithm, okay, for every polytime algorithm, there exists an instance for which the answer will be wrong. Instance of ILP, for the answer will be wrong. Right?
Yes.
Yes.
So there exists. Okay, this is very important. So it means that for, I mean, if you look at all the possible ILP instances that can be, not all of them can be solved by polytime. Right? But if somehow I am guaranteed something else, if I'm guaranteed that the instances that we are interested in are a certain kind, then there is possibly we can say that, oh, there might be a polytime algorithm. Is this kind of clear what I'm saying?
So,
can
if we were to reduce our input set, and we can show that, so essentially the reduced problem.
The restricted problem. Okay,
Right.
it's an IPLP for, say for example, vertex cover for general graphs is hard, right? Is NP complete. So possibly you don't have a polynomial time algorithm for that. But if I
Right.
tell you that the graph that I'm going to give you is planar,
Right.
then can you solve it? That is possible. Maybe possible.
We're reducing the problem to a smaller instance.
Right. We are restricting the problem. Right. We are restricting this problem. Okay. So you should always remember that it is not necessarily just because you have got to an ILP solution, it doesn't mean that that problem cannot be solved. Okay. ILP or vertex cover or something, in general, it is hard. But maybe it is easy for some setting. Okay. That's first thing to note. Okay. We will come back to this very fact a bit later on, maybe next week. Okay. But also the other thing can happen. Like for example, here we know the knapsack problem is hard is NP complete. So of course that means that the ILP instance that will be produced from there, that will also be hard. But okay, now what happens? We have this ILP instance. We don't know how to solve it in polynomial time. So what should we do? Any suggestions? How do you solve this such a problem?
Sir, maybe Lagrange multipliers.
See, the problem with Lagrange multiplier is exactly what the problem with ILP is, right?
Yes, sir.
What is it that this x's are not is discrete, right?
Right. Right.
But maybe that's what you are right. That is all about this thing. That's all. If only I had this
We can consider all possible combinations
of,
of this exercise.
that's a lot, right?
Yeah, yeah,
That is 2 to the power n.
yeah.
Okay, so that is one option, of course, but that is exponential time, right? So I want a fast algorithm to solve it.
Sir, maybe we can show that what optimization function we have.
Hmm.
It has such a property that if we were to assume that xi's are real,
Then also it solves. They give the right option. Very good. So that is another thing that happens, right? That maybe if I just can reduce, just say that okay, I would not write it 0 or 1. I will just write it as it is between 0 and 1.
yes. Sir.
Okay, and maybe that's what we can do. Okay, so this
Sir,
is
also, if we don't get a solution which is in this indicator form,
right.
maybe we can think of what is the nearest solution in that set, and we can show that it must be what maximizes it in this.
Wonderful. So you see, exactly, you guys are thinking in the right directions.
But we cannot say that. So if we are saying that it maximizes, that we are basically solving the problem, right? We can say
Cannot
that
exactly. We will not be able to say that maximizes. But can you say something else? Can you
we
come
can
up
say
with some?
it's a near. It may be
Almost an correct answer, right? An approximate solution to it,
yes.
right? And that is exactly what people do. That is exactly what people do. Okay. So first of all, this is the hard one, okay? So which means I can relax it.
Okay.
I just say that this is in 0 and 1. Now see, I am already in danger now, right? I mean, my answer, finally, your boss wants you to know whether he wants to buy the IPL advertisement right or not. You cannot say that you buy it with probability 1/3 or you buy it with the number. I mean, yes or no. I'll say I am telling yes 90% and no 10%. You cannot say such thing, right? You can make a decision on that, right?
Yes.
So but this relaxation is helping us. Why? By relaxation, I can solve it in polytime. So okay, very good. Let me relax it now and solve it. Okay. Now I get this relaxation. So these are numbers. Now I've found it. Okay. I've got a solution. Why? How can I get a solution? Because it's a linear program now, not an integer linear program. Right. And now it is up to you to decide what to be done. Okay. For example, do you want to think of this one as probabilities? If you want, you can do it. Do you want to kind of maybe, as one of you, Aniket suggested, that if the PIs are close to 1, I'll make it 1. If are close to 0, I'll make it 0. Yeah, that can also be done. Okay. And this is exactly what we do. And you have to prove that what happens. Okay, one option is to say that, okay, let's do this expectation. Let's think of this exercise to be 1 with probability P1. And now once we have that, you take x1 equals to 1 with probability P1, x2 equals to 1 with probability P2, and so on and so forth. You have an assignment of x1 to x6 to 0 and 1. And you want to say that, oh, this is the expected value or expected maximum stuff is fine. But maybe that doesn't satisfy the inequalities, right? But you can say the on expectation, most of the inequalities are satisfied. So I am not going to go too much into details here, but this is what I'm telling you. So this is a area that comes up. Okay. And there are various techniques that you can think of. And this is what kind of you can say. So if you, like, for example, do this with the probability, what you can say is that the expected on expectation, these inequalities are satisfied. But maybe on sometimes that I am not interested in expectation. I want these inequalities to be certainly satisfied. Then you can come up with some other strategy and kind of say that, see, I can give you an x1 to x, an assignment of x1 to x6 of 0 and 1, which will satisfy all the constraints. But the maximum value that I have to kind of achieve, I'm not saying that I will achieve the maximum, but I will achieve at least half of the maximum. Okay. So this keeps on happening, and this is, yeah, okay. So I don't want to go into this thing. So yeah, so this is what is the stuff that I will not be covering in this course, but I just wanted to kind of introduce you to this whole thing. This is what is approximation algorithms. Okay, so let me give you a problem in this respect, and you guys can think a little bit. You don't have to go back to ILP for that. But see, you have a vertex cover. I know that this is NP complete, right? So I want to solve this problem. Okay, so you have been given a graph G, and you have to output a vertex cover of G. Now, of course, and vertex cover is very easy to output, right? Take all of the vertices. Okay, so I want to say an vertex cover, say P prime of G. But I want you to guarantee that, okay, V prime is bigger than, sorry. So what is the vertex cover problem? Vertex cover problem, you want to minimize the size of the vertex cover, right?
Yes, sir.
I don't want you necessarily to do it, and prove that 2 times is less than 2 times the minimum size of vertex cover of G. Can you do it? Can you prove it? Can you come up with an algorithm, quick algorithm to solve it? See, note that if I had not given you this 2 times, okay, if I had just given you 1, meaning give me a vertex cover which is the minimum size of, which is size is basically, yeah, that whose size is the minimum size of vertex cover, or give me the minimum vertex cover. This would be hard, right? Because that would mean that you are basically asking the NP complete problem. But by allowing you to kind of find out an approximation, can you come up with it?
So something like if we try to find the number of matching, I mean the size of matching set. Not sir. So that would be more.
You are in a very good direction, so think about it. Okay, I let you guys to think about it in the class, at home, something maybe. Okay, just think about it. Okay, so so tomorrow, by the way, I will be taking not a class, but again a tutorial kind of stuff. And this tomorrow I will try to take it in class, in person. So if anybody is wanting to come to
Yes,
class,
sir. I'll go.
yeah, then I will be there. Okay. It's just a room 700, right?
Sir, so far we did not, I mean, we had only 2 or 3 classes in room number 700. So
Okay.
all the other offline classes, I mean, we are having only one online class, sorry, 2 offline classes each week.
Hmm.
So all of them have, I mean, among those classes, 2 or 3 were in room number 700. So there were some camera problems there.
Oh,
So,
okay.
so that's why we have shifted to room number 520, room number 523, I guess, and afterwards to room number 525.
Okay, so where
So
should
the
I
last, so you can talk to the associate dean. It will be better if you can just have a conversation with him and confirm.
Okay. So I will then send a mail to all of you guys, maybe hopefully half an hour before. Okay. So
Okay.
our tutorial class tomorrow is at 5 o'clock, right?
Right.
Yes. So I will be
Yes,
sending you.
sir.
Yeah.
Yes, sir, it's fine.
Go ahead.
Sir, and what will be the expected duration of the class?
It will be less. It will be 1 hour. Okay. So it will not be a class. It will be a
Okay.
tutorial.
Okay.
Okay. So, but I would like you guys to think about this this problem that is here of approximation algorithms for Vertex Cover. Okay. And any other question that is there for you guys. Okay. I am not giving you, I mean, just please go and, I mean, first of all, this total class people who are actually interested in this course seems to have gone down quite a lot, which I'm perfectly fine. Whoever is interested, I'm happy to teach that group of people. Yeah, I mean, so I will ask you guys to just take a look at the stuff that has been done so far, okay, and try to find out problems, questions that you want to ask me, okay, and if not, then we will have to do some small stuffs here and there, okay. But this is something that I want you to focus. So from the next week, I think there will be another 2 more weeks, right, or maybe 3 more weeks, forgot, of class after this.
I guess 3 weeks.
Yes, 3 more weeks. So then we will go to some other topic. Okay, so we have been doing this NP completeness and all of these things, reductions and all. So now that you have gotten some idea of what a P algorithm is, when is an algorithm hard, about questions about reductions and so on and so forth, we will go to back to some polynomial time algorithms, namely, this network flows and matchings and all those things from next week. Okay.
Okay, thank you.
Yeah. So you guys please think about this particular problem and come up with and have any questions that you have seen so far. If you want to discuss philosophy of this algorithms and all, I will be happy to talk about it. If you want to know something more, that's also fine. Okay. Okay. So any questions other than this? Whatever. Any more questions that you have? Okay. So if not, so good. So by tomorrow, I hope to get the questions, the midterm answers also out, midterm papers also out. Okay. So
Okay, thank you.
yeah. No, good. See you.
Thank you, sir.
Yeah.
Thank you, sir.